Alright, hello, welcome back. In this video, I'm going to be computing this integral not using the fundamental theorem of calculus, but instead using the limit definition of the definite integral. And although this is not a topic that is covered in AP Calculus, it is a topic that's oftentimes covered in University Cal 1 classes. And so it's just kind of one of those things that I would like to show you before you leave my calculus class, but I don't need you to be an expert on. Okay? And you'll see that this is, well, not nearly as nice and easy as the fundamental theorem of calculus, right? Because this one, we know where this one's going to go. We're going to bump up the power by 1 and divide by the new power. That'll be 2/3 x to the third as x runs from 0 to 1. So this integral is going to come back 2/3. So my job is to show that using the limit definition, which I think I'm going to need to write down here for you, that this goes back 2/3. Okay, so I'm just going to remind you that the definition of the integral from a to b of f of x dx is the limit of the Riemann sum as the norm of the partition goes to 0. So limit as the norm of the partition goes to 0 of the sum as I runs from 1 up to n of f of xi multiplied by delta xi, where this delta x could be different. You've seen the tables, right? The intervals are not always equally spaced. All right, so yeah, and that's going to be the definition. I think I'll leave it there. Okay. If you're more interested in that, I just recorded a different video on that, and that's elsewhere on the channel. So what am I going to do here? Oh, I'm going to write this as the norm of the partition goes to 0, which, okay, this is going to necessitate that my number of rectangles goes to infinity, which is going to actually make it a limit I can compute, but I'll just start with that. All right, well, what is f of x of I? Well, it's 2 times something squared, so I'm going to have to add up as, I runs from 1 up to n of something squared, well, 2 times something squared times a delta x. Well, delta x is b minus a divided by n, right? It's the width of the interval divided by n. I'm just going to assume equally spaced, or like even subintervals. So that's going to be 1 minus 0 is 1 over n. Nailed it right away. Okay, and then what are my x's going to be? Well, it'll be 0 plus I delta x. So it'll just be I over n. Okay. And yeah, I was looking at my notes, and I had actually, I think, a pretty useful note written. And so I'm going to go over here, and I think what I'm going to do is right here. Go highlight that in yellow. I'm going to write in, since f of x equals 2x squared. And what else did I write? And our integral starts at 0. I'll say a equals 0. The x's that I'm going to be interested in, xi equals 0 plus, well, I delta x, right? The first x is going to just be after I jumped over delta x once. So delta x is 1 over n times I, and also, f of x I is going to be 2 times, well, that's I over n. 0 plus 1 over n I. I'm just going to write that as I over n. We can write it like that. Okay, so that's where I got this from. All right, now, the really nice thing about this is that this is a sum over I. Okay, so what I'm going to do is I'm going to factor out the 2 over n squared, or maybe I'll just factor out the 2 over n right here. And I will acknowledge that this is the limit as n goes to infinity. But actually, hold on. I can factor out more than just this, this 2 over n right here. I'm going to actually factor out that n as well. Hold on. I'm not seeing that on my note sheet right now, but I'm going to pause and make sure there's not some reason I waited to factor the second set of n's out till later. No, there was no good reason. So I'm going to factor out the 1 over n squared here, the 1 over n, and the 2 because they don't have anything to do with my indexing variable. So I can rewrite this as 2 over n to the third times the sum as I runs from 1 up to n of I squared. Maybe I'll write it like that. Now, here's the thing. We can sum this. There's actually a formula for this. I learned about this in my pre-calculus class, but I taught pre-calculus once and that was not in the class, and I don't know where this fits in. Usually it's, I think we learned about this type of formula when we were learning about proof by induction, which is another thing that is not in the pre-calculus class anymore, but I think I'm going to just need to write the formula down for you. So, yeah, I'll just grab a different color right here and just give you a fact. All right. It's the case that the sum of the first n squares, which that's something you can type into Google and see, and they'll show you how to prove it by induction, but maybe there's another way, is the sum of the first n squares is given by n times n plus 1 times 2n plus 1, all divided by 6. Who knew? Okay. I did at one point, I just forgot. So I'll just say 1 plus 4 plus 9 plus ... up to n squared is going to be equal to, like I said, n plus 1, 2n plus 1, all divided by 6. Okay, but this is the sum as I runs from 1 to n of I squared, right? 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to n squared. That's exactly what this expression means. So I've got this fraction that I'm going to go back in and substitute here. Okay, so I've got 2 over n cubed multiplied by what's going to come back with, I guess I'll use yellow, n times n plus 1 divided by 6. And then you can see where this is headed, right? This is pretty much all over here. This is the limit as n approaches infinity. If I were to, multiply these all out, I'm definitely not going to do all of this, although I probably could. It wouldn't be too bad. Yeah, maybe I will. Okay, so that's going to be 2n squared becomes 4n to the third. I'll have 1, 3n's, 6n's. But all of this stuff isn't going to matter because it's only going to end up being the ratio of the leading coefficients, right, or of the highest power, so I don't really care that much. But I will just do it. Let's see, plus 1n is 2n. This is not on my notes, so if I made an algebra error, let me know in the comments, or just forgive me because it's not going to matter. It's only going to matter about this. Over 6n to the 3. And this limit is going to be 4/6, which is 2/3, which is what I hoped to show you in the first place. Okay, so this is how we compute a definite integral using the limit definition. Now notice, I used a function here that I already had this formula ready for. Okay, I don't know if there's going to be such a nice formula for non-polynomial functions, like transcendental functions like sine of x, good luck. I don't see that happening. Okay, I'm not saying that it's impossible to compute those integrals using the limit definition. It's just that for operations beyond squaring, the corresponding formulas for this get pretty unpleasant, and you just don't want to deal with it. Okay, so consider yourself, informed that this is how you would do it, but know that in my class, it's not going to really be a thing we